Let us illustrate the method of finding roots of a nonlinear equation with the help of bisection method. Okay. Now, as far as we know from the theoretical description of bisection method, the target is to fix up a interval for a given polynomial or transcendental equation fx equal to 0. It may be a polynomial equation, it may be a transcendental equation. By transcendental equation we mean an equation involving cos x, sin x, e to the power x, this type of functions which are itself an infinite series. Transcendental equation is defined to be an equation involving this type of expressions: cos x, sin x, log x, e to the power x. Now, fx may be a polynomial equation or a transcendental equation. We intend to find the root of this equation, roots of this equation by bisection method. So we apply Rolle's theorem of algebra or calculus, which states that if we have fa into fb to be negative, that means fx has opposite signs in these 2 points, then you claim that we have the roots lying within this open interval ab. Isn't it so? Because fa, either fa is positive then fb is negative, or fa is negative then fb is positive, vice versa. Since the product is negative, fa and fb has opposite signs. So if we draw the picture of fx as plotted against x, and if we point out the a point here and the b point here, we have assumed both of a and b as positive. It may so happen that a and b both are negative, or one is negative, another is positive. It's immaterial. But if a and if b are of opposite signs, that means either fa is positive or fb is negative. In other case, if fa is negative, then fb must be positive. And the point is of Rolle's theorem is that if fa and fb are of opposite sign, fx must cross the x-axis at least once. It may cross the x-axis more than once. If it crosses more than one, it must be in odd order. That means a and b contains odd number of roots. We say that ab contains at least one root. Okay, and we look for it, and we look for the root. So what is the crux of bisection theorem? Let me draw another picture and highlight the procedure once again. We said that fx equal to 0 is an equation, and we take, this is origin and this is x-axis, this is the positive side of x-axis and this is the negative side of x-axis. And if a and b are 2 points which contains at least one of the root, then we move on to work with this open interval a. How? We just bisect it. This is a plus b by 2, Isn't it so? See, if this is a and this is b, this is a plus b by 2. So our intention will be to bisect this interval and then test whether, why we have chosen fa and a and why we have chosen the interval ab, since fa and ab are of opposite sign, that I have clarified to you. Isn't it so? Since fa and ab are of opposite sign, that is, if fa is positive then ab is negative, or if fa is negative then ab is positive, we claim that fx equal to 0 has at least one root in the open interval ab, and then we choose the interval ab and bisect it. Our next attempt will be to establish that if we should test whether f of a plus b by 2 is positive or negative. Is positive or negative. Let us assume here, for the time being, that if a is positive and if b is negative. There is no loss of generality in assuming this. I have earlier shown you the picture here. I am repeating it. If we have these as x and these as fx, I assume that if a is positive and if b is negative, and we claim that this open interval contains the root, and we argued that since fx is continuous, it must cross the x-axis to reach fb from fa at least once. So this is our assumption, and there is no loss of generality. The other way around, if fa is negative and ab is positive, the picture will remain the same, more or less. So here we have assumed that fa is positive and ab is negative, and we halved the interval ab and bisect it at the point a plus b by 2. Then we check whether it is positive or negative. Just see that since fa is positive and fb is negative, if f of a plus b by 2 is positive, then we do not have the root lying in this portion. Isn't it so? We have the root lying in this portion only. That is, if this is positive, we have this to be negative. That is, a plus b by 2 and b, f of a plus b by 2 and fb are of opposite sign. On the contrary, if f of a plus b by 2 is negative, then if this is negative, then the root would have lied within this portion only. That is, if f of a plus b by 2 is negative, we would have fa into f of a plus b by 2. Product of them is negative, isn't it so? So we should check this only. After bisecting the interval, we should check this condition, that after bisecting the interval, which one of the bisected part, which one of the halved interval contains the root, and for that we should check this only. If this product is negative, the root lies between a and a plus b by 2, and if the product of fa plus b by 2 and ab is negative, then it lies within these two. So I hope I have clarified matters, and then we should again halve it. So a plus b by 2 plus b by 2, which gives us obviously the point as a plus 3b by 4. This is a simple calculation. That would have been our point through which we would have halved the interval again, and keep repeating this procedure. It is an iterative process, repetitive process, iterative process, so that we reach to the root of the equation. If we keep repeating, we would have reached a point where we got the exact root, subject to a level of tolerance. Let us explain this theory with a specific example. Okay? We will illustrate it with a very specific example. Just see, we are going to take this equation x cube plus x square minus 1 equal to 0. This is our fx. Okay? This is our fx, a polynomial, a very simple polynomial. This is a cubic polynomial, but this will illustrate the theory we discussed just now. How? Just see that here f0 is minus 1, negative, and f1 is positive. f1 is 1, so it is positive. It's very simple to check that f0 is negative and f1 is positive. Okay, so we choose 0, 1 interval to contain the root of this polynomial. We claim that a root, at least one root of it has three roots. This is a cubic equation. At least one real root is contained in this interval 0, 1. Fairly simple. So what will be our next task? What will be our next task? Our next task of bisection method is to halve this interval. This is 0 and this is 1. So this is the 0.5 or half point. So we should check where the root lies, isn't it so? And for that matter, we should first calculate f of 0.5. And it is very easy to calculate. If we calculate f of 0.5, it comes out to be 1 by 8 plus 1 by 4 minus 1. We don't need to exactly calculate the value. It suffices to conclude that it is a negative. And the moment we find that f.5 is negative, since we know that f0 is minus 1, so it is negative down there, and f1 is positive, and so that is why we argued that root lies here, and we find that f.5 is also negative. So the root lies within this, isn't it so, since this is negative? So we don't need to calculate this. So we move on to choose the interval. Let's not wipe out this picture. Let us draw it in a bigger way. This is 0 and this is 1 and this is 0.5, and now we are concentrating on this interval. Since f.5 is negative and we know that f1 is 1 and it is positive, so f1 into f.5 is negative. They are of opposite sign and the root lies in between this interval. So we tend to half it again. Now what is the middle point? We can easily find that the middle point is 0.75. Isn't it so? We can easily find that the middle point is 0.75. So we tend to find the value of f of 0.75. And it becomes minus 0.016. This value is rounded off to 3 decimal place. Okay, minus 0.016. So what does the root lies? The root lies between 0.75 and 1, isn't it so? So we again halve it, halve this interval. So what is the middle value of the interval 0.75, 1? This interval is again halved. So it is 1.75 divided by 2, isn't it so? And the point comes out to be 0.875. The middle of this interval 0.751. So we have to check the value of f 0.875, isn't it so? We have to calculate the value of f at 0.875. It comes out to be 0.4 positive. Then we can conclude that the root lies between 0.75 and 0.875, isn't it so? Just follow the logic. Since f of 0.75 is minus, but f of 0.875 is positive, so the root lies between these 2 points, not here. So our interval of concern is 0.75 and 0.875. Move on like this, then we should again halve it. So we should again halve this interval. What is the middle point of this interval? It is obviously 0.75 plus 0.875 by 2. Isn't it so? 0.75 plus 0.875 by 2. It comes out to be 0.8125. And again we should calculate f of 0.8125. Isn't it so? Only to find that f of 0.8125 is positive. And whenever f of 0.8125 is positive, since f of 0.75 is negative, our interval of, this is the middle point, 0.8125, isn't it so? And since this gives the functional value positive, we must have the root in between 0.75 and 0.8125. And then we should have it again. That means 0.75 plus 0.8125 by 2. What does it become? 0.75 plus 0.8125 gives us the value to be 0.78. 0.78. Okay? It comes out to be 0.78. And then we have to calculate f of 0.78 again. Only to find that 0.78 is again positive. 0.78 is again positive. So the root is in 0.75 and 0.78. Since 0.75 is negative. So these intervals, so we are narrowing the interval by halving it or bisecting it. We are narrowing the interval, and again we find that this is 0.75 plus 0.78 by 2. This comes out to be 0.765. This comes out to be 0.765. And we can easily check that 0.765 is again positive. Okay? So move on to choose the interval as 0.75 and 0.765. So we are narrowing in, and by repeating it, we would like to find the value of value of the function fx, which is almost 0. That is, the 2 decimal place after the point comes out to be 0. I hope if you calculate 0.7575, you will reach near the root of this equation. So this is the process how we highlight the process of finding the root of a equation using a bisection.